Hello, welcome to IFT ZK call again. Today's topic is arithmetic circuit representations for ZK. With this episode, we will cover all the necessary part of the zero knowledge. And yeah, Marvin, as always, stage is yours.
All right. As Uger mentioned, I will be talking about arithmetic circuit representation. As for all the necessary parts of ZK, well, we'll get to that. But these are fundamental for ZK snarks. So let's begin. An arithmetic circuit. Well, the first thing we want to know is what is an arithmetic circuit, and it's usually. I'm just going to go with the usually. It's a two inputs and one output. Lovely tech error. So if I make a tech error, I prefer to point it out so everybody can snicker. But one output, and it's addition and multiplication over a field. So this would just demonstrate a multiplication gate. So we have two inputs going in and giving us this C. So A times B equals C. Arithmetic circuits have been pretty much the popular circuits for ZK snarks for, I don't even want to guess how long, because I know I'm going to be wrong, but certainly like 10, certainly about 12 years at least when Pinocchio came out. Some earlier ones dealt with Boolean circuits, which would use AND and XOR gates. Some examples of that would be like ZK Boo. I believe the original Pinocchio paper actually talked about Boolean circuits a bit, but I'm a little hesitant to say on that one right off the top of my head. But certainly ZK Boo, because ZK Boolean is what's actually short for. But yeah. So kind of sporadically throughout this talk, I'm going to refer to this arithmetic circuit. This is an example. It's actually an example I snagged from I believe Pinocchio in their appendix, but this is just a simple one. There's there's a single addition gate, two multiplication gates, 4 inputs total, and 1 output. You can have much more elaborate arithmetic circuits. To give you mentally an image of one, you could imagine Poseidon. If you work with Poseidon hash functions, you can imagine that entire all those operations being laid out as a massive arithmetic circuit. If you also, since you can actually represent ands and ors in terms of addition and multiplication, you can really represent anything in a computer as an arithmetic circuit with the and and or with the Boolean restrictions. And when you do that, what you actually have happen is you could then represent something like SHA-256 as a giant circuit. Obviously, these are massive circuits, but just to give you some ideas. Now, this particular arithmetic circuit just represents the linear equation y1 equals x1 plus x2 times x3 times x4. Pretty straightforward. You're just tracking these wires to get the x1 plus x2, x3 times x4, and then this final multiplication. Okay. So, arithmetic circuits, that part makes sense. We need to connect this to zero knowledge. We've been talking about zero knowledge, obviously, for every ZK call, or at least tangentially. But how does this really connect, essentially? Why would we do this? I think there was a question.
Yeah, there's just one question right now.
You can go ahead and ask it. I heard Dean.
Sure, of course. in slide. Yeah,
sorry.
you can go. Yeah.
I posted the question. I didn't want to interrupt your flow. Feel free to answer it when there's a suitable pause. It's related to how the arithmetic circuit and an abstract syntax tree can be compared in terms of the mental model of what they are. So feel free to answer when you want.
How the arithmetic circuit and the what compare?
Abstract syntax tree.
Can you describe what abstract syntax tree is? I apologize. I'm a mathematician, not a software engineer. But so no, you're fine on the interrupting the flow. Like this would be a different topic.
Okay, cool. So maybe an abstract syntax tree is like the software equivalent of the mathematician's arithmetic circuit. It's basically when you take the syntax of the or actually semantics of source code that you write, and the compiler toolchain breaks it down into a form where you do a sequence of operations that looks like the diagram of the arithmetic circuit.
Okay, it's kind of like that trace execution. It's yeah, like back in the old days, this would be the old days when people actually drew out the diagrams of the workflow. I don't know if you ever had to do that for a program with okay. Yeah, I know what you're talking about. Basically, it's you've written your source code. Well, I think I know what you're talking about. You've written your source code, and it's kind of how the compiler translates it. I mean, you're not quite going to the bytecode yet. You're talking about like that semantic workflow though, like how it deals with the memory. But in your source code, you have all these parameters. Some of them are variables. Sorry, some of them are user defined or hard coded. Some come from user input, and some of them are manipulated essentially, right, through the computation. And I'm trying to not misspeak in terms of I'm trying not to insult any software engineers with my misphrasings. But yeah, so all these variables that are being manipulated by the source code, in terms of those trace executions and memory accesses, you could basically view them in the same way as an arithmetic circuit. So for instance, this one was like hard coded by the program. This is a user input like at the beginning of the program. Then this operation just kind of says how, like, what's going on. Maybe down here is like a memory access changes and stuff like that. So you could still map them to what you're thinking of, especially if you're viewing this as a Boolean circuit, because like I said, a Boolean circuit, everything in a computer can be represented that way. So if instead of having X1, X2 and all that, you literally have your bits all written out, which sounds terrible when I phrase it that way. But you have all your bits written out and you're kind of looking at them as in bit operators. Obviously, you could group bytes together because most people don't work on individual bits often, but hopefully this is kind of saying yes, you can view them identically.
Does
that make sense?
It looks a lot like. I wouldn't be surprised if this is a copy paste of a diagram that is introduction to abstract syntax tree. So it'd be interesting to talk. It might be interesting to talk a bit later about what the different views into these constructs are. Mine from the software engineering background, and yours from the mathematician background.
Absolutely, we can. But yeah, you are absolutely correct that this is probably copy and pasted. A lot of the papers that started talking about this stuff originally are actually more software engineering papers, and they're looking at terms of Boolean circuits, because once you start doing finite field operations, you've shifted away from this very, I want to say abstract level, but you made it more specific. You essentially, this X1 now becomes like 32 bytes instead of like 1 byte, and stuff like that. So it's definitely a copy and paste application. But yes, we can sync on this later, and if you'd like.
Look forward to it. Thank you.
Okay. Does that make sense to everybody else? I'll take that as yes. All right. So a zero knowledge proof that we have been talking about all the time, it essentially boils down to me saying this statement is true, but I'm not going to tell you why it's true, how I know it's true. I'm just going to convince you that this statement is true. So we are demonstrating the validity of this. Now a statement has to be in terms of some underlying relation or circuit. So for most ZK snarks, you are talking about a very specific circuit. So if you're talking about GROT16, GROT16, as we've mentioned offhand many times, it has a circuit specific construction, which means a GROT16 proof is tied to that specific circuit. So in the original version of Zcash for Sprout, GROT16 was used for transactions. So you would say that, here's a valid output of the transaction, but I'm not going to tell you the inputs, but here's proof that is correct. In terms of our arithmetic circuit, my statement could be the circuit can produce 21. And you go, okay, well, there's many ways to produce 21. I could potentially tell you all of the numbers, or I could tell you none of the numbers for X. So maybe, I tell you like X3 and X2, and I go, yeah, there's some X1 and X4 that will produce 21, given that X2 is 5 and X3 is 1. It kind of depends on how the underlying ZK snark is set up, but the circuit gives you that initial framework so that the prover and the verifier are on the same page of what statement actually means. Okay. So when you are designing a ZK snark, it's basically assuming a specific arithmetic circuit representation, and you might do some arithmetizations on it, which kind of deals with a little bit more of the polynomial stuff, which we won't be diving into, just for, again, keeping this as friendly as possible. All right. Oh, and speaking of misspellings, looks like I misspelled arithmetization probably a few times in this. But anyway, so one of the earlier ways to kind of arithmetize, I mean, it's still correct to use it this way. I just prefer to think about it in terms of polynomials portion. But to arithmetize an arithmetic circuit is with something called a quadratic arithmetic program, a QAP. This was actually introduced, I believe, in Pinocchio. And it deals with addition gates and multiplication gates. The addition gates are collapsed essentially into a constraint for the multiplication. And they given an arith. So when we collapse all these together, all we care about are the constraints that are represented in terms of our multiplication gate. So if we go back to our arithmetic circuit, we have an addition gate right here. So you go, okay, well, since we have this written here, we'll go with this side first. Okay, so I have X3, I have X4, and they go into a multiplication gate. So these would give me a single constraint because I can multiply this together. Then with these two going into this multiplication gate on the left, this is going to give me another polynomial essentially that's going to get multiplied by that W1. So I end up with x1 plus x2, that gets collapsed, then times. So if I had like another one like x5 being added right here, it would just be x1 plus x2 plus x5. Only the multiplications will remain. The additions again get collapsed. Obviously, there are spots where you might have addition at the end or at the at the beginning where not much you can do about it. That will kind of hang around, but for the most part, they'll get collapsed. All right. So quadratic arithmetic programs are kind of nice. They were used for like Rot 16. They were used for Pinocchio, but they've kind of fallen out of favor in the last several years. And they've fallen out of favor for R1CS. R1CS is rank 1 constraint system. I don't actually remember what they mean by rank 1, other than it's not what I want rank 1 to mean as a mathematician. I remember seeing it back in the day, and the only part about it that stuck in my head is that it's not matrix rank 1. So I apologize, I don't remember that, but but if you took linear algebra and you remember ranks of matrices, that's not it. Anyway, rank 1 CS is basically QAP with matrices. Instead of having polynomials, we're going to represent essentially everything as matrix multiplication. So from our QAP, we had this. So what we need to do is we will represent the first product as a row in my matrix. So for this first one, I just have an x1, an x3. So I put 1 in the x3 spot. And for the second one, I have a x1 plus x2. So I put it in this spot. So when I multiply matrix A times this vector, it will give me the x3, and it will give me the x1 plus x2. And I can do a similar thing to get a matrix B. And what that will do is, when I multiply, it will give me x4, and it'll give me this W1. So we have a way to nicely represent our multiplication. And then with our other side of the equation, we do the same thing. I just need to represent W1 and Y1. And this gives me a very nice linear way of representing this constraint. This is identical, essentially. It's nicer to represent in the computers. It's not necessarily the most intuitive in some ways, since you'll have to translate it to polynomials to some extent, which I have written here, so I don't know why I'm going anywhere. But this is the kind of preferred way to do it. So if you're looking at some of the more modern write-ups for like Grot 16, you'll see them say it's R1CS. The original paper will, of course, be a QAP, but they're essentially the same. I'm trying to think of ones that are explicitly R1CS in the original papers, and I am blanking because I believe Aura is R1CS. Most of them are R1CS. I'm just having a silly moment, but most of them are. Squaring arithmetic program it's weird because I believe it predates R1CS. Oh, another R1CS, bulletproofs. There you go. But squaring arithmetic programs is different in like a couple ways, but one major way. Instead of having multiplication gates, we represent everything in terms of squaring. So I don't have any multiplication gates. Everything's a square. So if I want to represent my arithmetic, like my normal gates with multiplication, I have to do this strange arithmetic trick. So a times b is actually the difference of two squares divided by 4. So you have to start adding in additional operations. So what that means is that for every n multiplication gates, you're going to have to replace it with at most 2n squaring gates. The reason at most is maybe the same square gets used twice and you can be lucky. So there's that. Okay, yeah. Now, where squaring arithmetic programs are used, so there's a paper by Grott and Mary Mallard from 2017 that introduced this. It's briefly mentioned in Grot 16 as a throwaway line that you could, use squaring gates instead. Not formally mentioned, but it is mentioned. So squaring arithmetic programs aren't formally introduced, but it's mentioned you could do it. And more recently, there's been a couple of papers using it. Specifically, there's a paper for pair, P-A-R-I, that came out last year, and the interesting thing about pair was that it gave you a way to use squaring operations to get a smaller byte size for your pairing group ZK Snark. So Grot 16 is the smallest in terms of group elements, but if you relax some of your requirements, you can get, and you look at in terms of the concrete space size, not the theoretical math objects of group elements, but the bytes that it takes up in the computer, you can get smaller by, I think, about half maybe. But a pretty substantial size difference. And Perry does that using the squaring version for R1CS. And Polymath might actually use squaring arithmetic programs to do the same type of thing as well. All right. Any questions yet?
No, yet.
Okay, just making sure.
So,
Yes.
I've got a quick question. Maybe I missed something, and I apologize if I missed it. But if I was to read this correctly, the advantage here is that we're replacing multiplication with squaring, and squaring is inherently a more desirable operation. I'm assuming I've got that correct, yeah?
So it's a very strange thing. It's a very reasonable question. I didn't say why we were replacing it with squaring, because if you look at it and go, oh, I've increased my number of gates from n to 2n, to me that sucks, because if we think about R1CS, which, like I said, was a QAP essentially, our number of rows was based on the number of multiplications, because we had 2 multiplications, so we got 2 rows. So if I were to do this, I would have 4 rows if I were to expand my my arithmetic circuit out to use SAP. So that would, kind of suck. Now, you have the real answer to your question of, okay, we have all these arithmetic circuit operator representations. We have, R1CS and QAP, those are equal. So I would probably just end up using R1CS because that's going to be what the libraries are really written in. That's what people prefer. So, QAP, that's one of those weird math oddities. The squaring arithmetic program, that's different. So why would I use that instead of R1CS? That's kind of like the root of the question, to some extent. And the answer to that is the representation that is kind of that you would use as a software engineer is essentially imposed upon you by what ZK snark you're using. So if you were looking into using something and you go, I'm using a circuits. I'm using a system that's going to be constantly using the same circuit. I don't care about changing any circuits. Then you go, okay, well, I'm never changing my circuit. This is like, potentially an early version of Zcash. Also, I realized I misspoke, so I'm going to correct myself. Zcash Sprout did not use Grot16. It used Pinocchio. We had talk on that a couple months ago. I'm sorry, I'm an idiot. Sapling used Grot16. So for anybody that knows that I made a dumb comment, there you go. But anyway, so if you're in an application where you are doing something that's circuit specific, that you're never changing the circuit, you would go, okay, I want to have this as efficient as possible. You would look at something like, Grot16, but then you might look at, going, okay, Grot16's nice, but, I could sacrifice a little bit of proving time for really having the smallest on-chain storage. And that's where you would go, maybe look at Perry, and that's when you go, okay, am I willing to take the advantages of having a smaller concrete proof size in terms of bytes by using the squaring gates? Because, like I said, it's going to increase the computational size since you're increasing the number of gates that you're working with. But if you've got like a smaller proof size, then you would use it. Now, is there a good theoretical reason to use squaring gates over multiplication gates? I think it's one of those things where if you stare at the problem long enough and you can see something really super amazingly slick that you can do that makes something smaller, then you go with squaring gates. But outside of that, I'm not sure there's a good reason. So to summarize, for software engineers, you use what your design specs would force. You select a ZK snark based on your design specs and requirements, and that ZK snark is going to force your circuit representation. And for theoretical construction of other ZK snarks, you do black magic. Is that vaguely satisfactory?
Yeah, I found it quite interesting, the comment about the trade-offs, like on-chain. Some aspects of this process on-chain is much more expensive, and taking the squaring approach can minimize the things that are much more expensive on-chain.
And the explicit reason why pair minimizes, I had looked into back in the fall. I don't remember the exact reason, but that's something we can talk about later as well. If you want to dive into that, we can, the math on why that actually does give you a cost savings. I don't have an answer off the top of my head on why it does it, other than saying via theoretical black magic. But
It's mathemagical.
yeah, I prefer black magic, but that's more because I can't pronounce words. But yes.
No, very, very interesting. Very interesting. Thank you.
Yes. Okay. And the last one we're going to talk about is probably the most popular at the moment. We'll go with second most popular. I think R1CS might still win. And that's Plonkish. Plonkish is named after, Plonk. And because every time I comment on this, there's a new update. They've updated the paper back in, if I remember how months work, March. Yes, so there's been a new version of Plonk since March. I think it's just some minor like citation updates, but yeah, I'm just always amused when I go look. There's a new version, but that's neither here nor there. Anyway, so the Plonk representation, what it does is each gate is represented individually, and it's represented by this type of equation. And if you look at it and you go, okay, well, clearly, as I've written down here, we can see addition gates. All I need to do is ignore this portion and this portion, and I have an addition gate. Like, I have A plus B minus C equals 0. Cool. And if I throw away this portion and this portion, I get, I'm left with just the middle being a multiplication gate, assuming you plug in ones in the appropriate spots. So that's cool. But I can also represent kind of more things than just that. Now, with that said, we should point out that it's not as expansive in some of the ways. Like, it doesn't collapse all the addition gates down like we saw with R1CS. So this is completely distinct to R1CS. Because R1CS, we could have an addition, but we couldn't have a multiplication mixed in. And we right here, we're limited to just 2 additions. But we can have the addition of 2 values that are the same with the multiplication of those values. So you actually get kind of more things. You get the support of custom circuits plus this constant. So we get XOR. So with XOR, we can and just clarify, we can represent XOR with a single constraint instead of a bunch of constraints that we would have had to do in R1CS. So with this, I'm able to represent it in a single equation with it as, so if I wanted this to be 1, if A and B were 1s and 0s, then I can check this and go, okay, if they're both 1, let's see, so XOR, so one or the other, not both. So yes, what that would do is if both were 1s, then this should be 0. So 1, 1 minus 2. So that's 0 plus 0 plus 0 is 0. So that's good. And if I had just one of these as 1, then 1 plus 0 is 1. 2 times 1 times 0 is, 0. So I have 1 plus, and then obviously if I have 1, the correct answer from 1 or X or 0 is 1. Can't speak. So this is 1 plus 1, but this should be mod 2. So 1 plus 1 is 0. So yes. So that checks out. And I can also, write some weird linear expression as well. So, because there's no restriction essentially on what these coefficients QL, QR, QM, QO, and QK are. Now, if I had a bunch of these for our arithmetic circuit, I could, go through and, write each one out I didn't, mainly because I wasn't convinced I would have the time. Sometimes questions are longer than others, but yep. So, but I could go through and write each of my gates as one of these. And if I did that, I had 3 gates. So I had 1 addition gates, 2 multiplication gates. I would have 3 equations for this. And you could represent it with matrix multiplication again, where QL, QR, QM, QO, and QK are all matrices, and the A, B, and C are vectors. Making sure that was right. Yes, that's correct. So that gives you another way to represent it. Plonkish is used by, obviously, Plonk, as I mentioned, and Halo 2. I believe Plonky 2 does not. I think Plonky 2 does not use it. Plonky 2 is one of those ones I always I've looked into, but not well enough to have it off the top of my head. Let's see. It uses FRI. I think it does use Plonkish circuits, but I'm not going to swear to that. But it uses FRI for the arithmetization, so the additional steps. But yeah, so those are the main ways you essentially represent your arithmetic circuit for computers and to do your ZK snarks. As I mentioned earlier, the ones you select is essentially the one that your software system's telling you. Mostly you're going to see R1CS, you're going to see Plonkish as well. Plonkish and R1CS are basically the same. There's a model that unifies R1CS and Plonkish together. I don't remember the abbreviation, unfortunately, but there is a circuit representation model that unifies both R1CS and Plonkish, so that they are actually just special cases of this overarching one. I don't think there's any concrete reason for software engineers to care about that unification, because at the end of the day, like I said, the one you use is going to be what your ZK snark tells you. But this was just a kind of quick and dirty, what are these representations? How are they kind of a little bit different? And why should you care? But I'm happy to answer any questions.
Yeah, there's no in chat.
I think I've got a question. I'm just trying to formulate it quickly. From what I'm seeing, there's some rearrangement of how you're putting together gates, and something that is cropping up in my mind is if there can be some sort of implications in terms of in silicon optimizations. So, for example, division is a very expensive operation in terms of feeding that operation through the logic network of the CPU. And there are some operations that are super fast, like multiplication of 2 is just a bit shift, or multiplication by a power of 2 is just a bit shift. Whereas multiplication of arbitrary numbers is nonlinear. Is there any possibility that with these changes that it could open up the doors to circuits that on paper would appear to be much less performant, but given that they change what the gates are, they could leverage in silicon architecture to ultimately be more performant. Is that
so it's a little tricky because the thing you also have to keep in mind is all of this is like when in terms of like ZK snarks, you're thinking about x1, x2, x3, x4 as build values. So not only are you, when you're doing your multiplications, are you necessarily having to do the nonlinear multiplication that you mentioned, but you also have to do the modulus, which is kind of dealing with division to some extent. I'm not sure the optimization formulas that are necessarily used to make that a happy scenario, but I mean, like, I think, and depending on the package that you're using, the size of these scalars can differ. So it, certainly you could look at some of these that's like, 64 bits, I believe, which, is already, kind of obnoxious for some CPUs to handle. There are, formulas that you can use to make that more tractable. But I'm not sure there's a better. So if you write your arithmetic circuit down, I'm not sure there's going to be necessarily a good way performance wise you can make it, run better in a CPU other than, don't have a really bad representation. Which, I mean, you could have something where you could simplify it down a little bit. Maybe there's redundancies and whatnot. Because at the end of the day, most of these arithmetic circuits that people really deal with are generated via like something like CircCom or NOR, which will like just go ahead and generate these circuits for you, and then you feed them in. So those are presumably fairly well optimized, but maybe you find like an edge case where it produces something really terrible, or more realistically, you used the very old version and you used an edge case that has hopefully been patched out. But most of your, I think, computational limitations that you're going to run into is actually not going to be on the arithmetic circuit side, but it's going to be on the polynomials that you would actually work with, because all these polynomials, all these quadratic circuits. So like with R1CS, we have all these as matrices. And in the last ZK call, I had talked about how given a matrix, you can represent it as a multilinear extension. So you transform this into a polynomial. And once you transfer this into a polynomial, and then you start doing, essentially some of the polynomial arithmetic on it, that will be presumably a lot more costly than the, CPU-based arithmetic operations on, scalars would do. So, does that seem reasonable?
Yeah.
Okay. I mean, great question. Is, but yeah, I think the other steps are going to be like what is very costly. But I think you are hitting on the points that essentially makes proving very difficult on consumer hardware. Something that comes up quite a bit, and potentially with your tests as well, you may have seen that, proof generation on consumer hardware is not necessarily friendly. There are, instances where you can do it, certainly, but it very rapidly gets out of hand. But yeah.
Also, let's add this. This summary of this presentation will be on forum.vacdev. So if you have questions, not only from here, also for all auditors. So yeah, you can check from there too.
Mm-hmm. Yes.
So,
and by the time this video is up, that forum post will be up too.
Yeah, sure. And I think there's no more question. Thank you, Marvin, and thank you for listening. So yeah, see you on the next episode.
Thank you very much. I enjoyed that.